Hello everyone, my name is Qinghe. Today, I will be presenting a paper titled StreamMem, Query Agnostic KV Cache Memory for Streaming Videos. Before diving into the technical details, let's quickly look at the motivation. Multimodal large language models are extremely powerful, but they heavily struggle with long streaming videos due to severe memory and compute constraints. To address this, StreamMem proposes a training-free method to compress the KV cache on the fly using a combination of filtering, attention pruning, and merging. In today's agenda, I will first walk you through the background on the StreamMem pipeline, and then spend the second half of my presentation providing a critical analysis of its novelty and limitations. To understand where StreamMem stands, let's first review how current MLMs handle streaming videos. Streaming requires the model to process frames continuously without knowing the end of the video. Several works have tackled this. For example, Video LLM Online focuses on real-time dialogue capabilities. RKV introduces a strategy to encode the video streams and offload the KV cache to disk or memory, retrieving it only when a question is asked. More directly related to our topic are Live VLM and Infinite Pod V. Both works focus on KV cache compression. Live VLM reduces memory usage to speed up question answering, while Infinite Pod V combines temporal redundancy reduction with norm-based selection to maintain a constrained memory budget. These works set the baseline for bounding memory in continuous streams. Now let's look at the general long video understanding. We see a clear evolution. Early models like Lava could use the process a handful of frames, leading to massive information loss. To fix this, many training-based methods were proposed to reduce the number of visual tokens per frame. Recently, powerful methods like Gemini and Qwen 2.5 VL have built-in long context capabilities. However, fine-tuning models for long videos is extremely expensive. Therefore, the current trend favors training-free methods. These methods directly compress visual tokens or the KV cache at inference time. The beauty of training-free methods is their plug-and-play nature. You can apply them to any newly released MLM without retraining. Since StreamMem is essentially a KV cache compression technique, let's look at how this is done in text-based LLMs. Traditionally, methods leverage cross-attention weights between the user query and the context to figure out which tokens are important. However, recently, researchers realized that this doesn't work well for streaming, so they explored query-agnostic mechanisms. For instance, Zhang and Arif used the attention weights of the CLS token to decide which KV cache to keep. Other methods use task-specific proxy prompts. This query-agnostic concept is exactly what StreamMem builds upon. So why is processing streaming video so difficult? There are three main bottlenecks. First is memory explosion. As you can see in the bar chart, long videos generate tens of thousands of tokens. If we keep all of them, the KV cache simply blows up and exceeds GPU limits. Second is the offline processing assumption. Traditional methods assume you have full access to the entire video before answering. In streaming, frames arrive sequentially. Third, and most importantly, is query awareness. Standard compression keeps tokens relevant to a specific question. But in streaming, the video is playing before the user asks a question. We don't know what they will ask. Therefore, we must compress the video in a query-agnostic way while strictly adhering to a bounded memory budget. This brings us to the core of the paper, the StreamMem pipeline. It consists of four step-by-step components. First, filter frames. As the video streams in, the model merges highly similar adjacent frames to remove basic temporal redundancy. Second, KD cache. Here is the most critical step. Since we don't have a user query yet, how do we know which tokens are important? StreamMem introduces a proxy query. They use standard chat template tokens like system prompts to approximate user intent and rank the visual tokens, keeping only the top K. Third, merge tokens. Instead of completely discarding the non-top K tokens, it aggregates them into a visual prototype to preserve some background information. Finally, bounded memory. The surviving tokens and the prototypes are stored in a fixed size context window. They also apply a YAM fix, a positional scaling technique to ensure the model's positional embeddings don't break when sequences are truncated. This whole process runs dynamically as frames arrive. Let's look at the performance. On the left, we have offline benchmarks like MVLU and the video MME. The dark blue bar is the StreamMem, and the black bar is the full cache baseline. As you can see, StreamMem almost closes the gap with the full cache models, performing significantly better than uniform sampling. On the right, we have streaming benchmarks. Here, StreamBatch is highly competitive with sought-up streaming methods like InfiniPod-V and LiveVLM. The key takeaway from these charts is that StreamMem achieves strong performance while maintaining strictly bounded memory usage. Now, I would like to transition to the critical portion of my presentation. While the results are solid, from a research perspective, StreamMem suffers from incremental novelty. If we break down its pipeline, almost every component is borrowed from prior knowledge. Frame filtering is similar to long VU. Attention pruning is directly inspired by SnapKV and H2O. The token merging and the prototype concept was already done in LiveVLM, and the positional scaling is just a YAM. The only somewhat unique element is using chat template tokens as a proxy query. Ultimately, StreamMem is a system-level engineering effort that stitches together existing building blocks rather than introducing a fundamental algorithmic innovation. Furthermore, let's examine their biggest contribution, the proxy query. There is a fundamental flaw in this assumption. Because the proxy query uses generic chat templates, it essentially acts as a basic saliency detector. It retains large, obvious moving objects but discards background details. This means if a user asks a fine-grained question, for example, how many times did the man in the background check his watch? StreamMem will fail because those unimportant details were pruned away before the question was even asked. Look at the chart here, the true queue, where the model knows the exact question beforehand, performs noticeably better than the proxy query, especially on multi-detailed tasks. This shows a clear upper bound to their query-agnostic approach. Another significant limitation is hyperparameter brittleness. Specifically regarding the lambda factor used for positional scaling, the system is highly sensitive to this value, and it requires entirely different tuning for different foundation models. For instance, Lava needs a lambda of 8, Quen 2 needs 2, and Quen 2.5 needs 1. As the chart shows, if you pick the wrong lambda, performance swings by about 5 points, which is a massive drop in this domain. Additionally, if we look at the base size, StreamMem scores 65.9 compared to InfiniPod V's 65.8 at the same KV size. This means after all this complex tuning, the competitive advantage over existing works is actually quite marginal. To conclude, let's summarize the takeaways. The strengths of StreamMem are clear. It addresses a very real-world problem, streaming with bounded memory. It provides a simple plug-and-play solution without requiring expensive retraining. However, its weaknesses are that it largely stitches together existing techniques. Its a proxy query discusses fine-grained details, making it unreliable for complex questions, and it suffers from hyperparameter brittleness with only marginal gains over baselines. For future work, I believe the field should move beyond fixed generic proxy queries. We need adaptive semantic memory that learns to preserve pertinent details, as well as dynamic memory allocation rather than rigid top K pruning. Finally, these models need to be benchmarked on much harder scenarios like multi-speaker interactions or tiny objects. Thank you for your time.